So what we see here is our next exercise about integral calculus. It's number 2, and it consists of these 3 different indefinite integrals, as you can see them here. And the aim of this exercise will be to learn a little bit about the very broad technique called substitution. Substitution, in this case, because we're dealing with one independent variable only, so it's a substitution of the simplest kind, if you want, because we just have to find an appropriate new variable which replaces the original variable x, so that the function under the integral, which is called the integrand, gets as simple as possible for us to be able to find its primitive, its antiderivative, as you know. So that's what it's about. So now looking at this fraction first, this rational function, it strikes you probably that the expression in the numerator is linear, while in the denominator this term is quadratic. So it might be a good idea to try and get rid of this quadratic expression in the denominator, always aiming at finding a substitution that helps us to solve this integral by just simplifying the expression. You know, it's otherwise, in case you would not, or just imagine the whole substitution technique would not exist. So the only chance you would have is finding, just by trying, finding a function which has a derivative equal to this rational function here. And now that's one of the reasons why integration is usually said to be more difficult technically than taking the derivative, like differentiation. Because when differentiating, you have a very small set of fixed rules that you can always apply. While when performing integration, you are forced either to guess which function it is that has a derivative equal to this integrand, or otherwise to simplify it by use of substitution and things like that in order to solve it directly. So that's what we want to try here. Now, idea and also a proposition approach. Since the factor of 4 is can easily be extracted or even split, what about taking 2 times 2 equal 4 and then pulling one of these factors outside of the integral? This is well, a step that I can always perform, because constant factors are never concerned about the integration, or they are not affected by the integration, as you know, right? So if I just say this is 2 times 2 times x in the numerator, one of these factors outside, and looking here, I see this is exactly the derivative of the denominator term. And now comes the standard substitution. I'm explaining this a little more in detail because it's the first time we're talking about it, right? So look here, I say substitution, colon, I choose u to be equal to x squared plus 1. So that, and now this is what you should be familiar with already. Oh, I'm sorry, I forgot the differential here, times dx. So the idea behind is you can interpret this new variable called u as also as a function of x. It's quite simple. Even if x is the only independent variable in this whole exercise, just imagine x takes on values starting from whatever, let's say 0, and then it's increased, okay? And by increasing x, you will find that u also increases. So it's clear that u is as well a valid variable. It can also be used as an independent variable instead of x, but also you can interpret this variable u as a function of x itself. So if I just imagine, I would be saying u of x, like u as a function of x, and then asking what is the rate of change of this new variable in relation to a change of x. And now the derivative u prime of x, sort of, right? Or in other words, du by dx, du over dx, I should say. I just put it here. If I say u of x equals x squared plus 1, then I can say, okay, in this case, the derivative in differential differential quotient notation would be du over dx. And this is simply 2 times x, and that's it, as you know, polynomial, okay? Regular rule for taking the derivative of a polynomial. The additive constant disappears, the squared term gets this linear term. You know, we've done this before. Now, the idea is to separate the differentials now in the next step, so that I say, I can conclude that there is a certain connection between a differential increase of variable u compared with an according differential increase of variable x, as you see here. So, and this is something that's very important for the substitution, because if we introduce a new variable here, we must also adapt or adjust the differential as to be expressed by the new variable, so that we need an increment of the new variable instead of the old. And that's why we need this connection. This is very concrete. I could give you a numerical example. Sometimes it helps to understand that this differential equation tells us more than just saying this is, you could say, almost zero, because it's differential, and in the limit, these differential elements are always approaching zero. So this is like 0 equals 0, but that's not what it is. It's more than that. It tells you how fast or how strongly the new variable will increase if you increase the old variable x by a certain amount. Okay, I could give you a numerical example, but I'm sorry, I'm just I don't have the time right now. Okay, let's just believe it, and then you see that what I'm doing next is I consume, you could say I consume this expression 2x times dx, which is in the numerator, right? This 2 times x times dx is exactly what we found here, so I can replace it by du, by a differential of the new variable. And also the term in the denominator gets just simply replaced by u. So all that remains is factor of 2 outside times integral now 1 over u du, which is really simple and well known. And we all know that in the indefinite case, the primitive function of this reciprocal 1 over u is the natural logarithm of absolute value of u. Please always, or the other way around, never forget to place the absolute value sign, these vertical bars. It's important for a simple reason. This function is defined everywhere. Let's forget about x for a moment, right? So our new variable, okay, I must admit, in this case, it turns out that u can never be negative. This is due to its definition by using x. You see, this is a positive term. It can never be lower than 1, actually. So in the end, here, the signs for the absolute value will be superfluous in the end. But imagine you would not have had this substitution before. If this is your original integral, you would not have a restriction for u. And then this reciprocal function is defined everywhere except for u equals 0. So since we know that this is the derivative of the natural logarithm, we have the problem that the natural logarithm is just defined exclusively in the positive domain. So, but this way, when taking the derivative, we never ask about the domain or let's say about the negative domain, because it doesn't make sense. But in this case, we have a function, an integrand, which is defined almost everywhere. So it should also have a primitive function in the negative domain, and it does. So, and what it, as you see, in this case, it will be the even version, you could say it's a completed version of the natural logarithm in the way of an even function. I should just jump just for a moment to one of the next exercises where you can, by chance, you can see the graph of this function. It's the last one actually about improper integrals, looking here. So now this is something else. It's about finding the primitive of this, but it's more or less the same thing. And you can see the graph of this interesting function ln of absolute value of x, if you just make a case distinction and say it's just ln of x in the positive domain, but it's ln of negative x if x is negative, because negative x in this case gets positive, and what you have is altogether, look at the blue graphs here. This is our well-known logarithmic curve for natural logarithm. This one is its counterpart in the negative domain. Like what you do is an axis reflection on the y-axis. So you get an even function, which is the completed version of the natural logarithm. And also, just looking at the blue curve, it's these two curves, okay? It's the full, well, description of the rate of change of the reciprocal function. Is that right? No. It's not. It's the opposite. It's the sorry. It's the primitive. Yeah, it describes the area between the reciprocal function and the x-axis in the negative domain as well as in the positive domain. This is what I wanted to tell you in case you are having problems from time to time. Why is it always important to have these vertical bars? Now I hope it's clear. But on the other hand, we have to perform a resubstitution. We should always resubstitute in the case of an indefinite integral. So that's what I do. I replace u for or against x squared plus 1 again, right? And then I find that this expression is always positive. It's even greater or equal than 1, as you see, due to the squaring procedure. And that's why I can replace the vertical bars in the end by regular parentheses. I have to add already here an arbitrary additive constant. It's the famous integration constant, because as we all know, by the fundamental theorem of calculus, it does not matter if I perform a test and take the derivative of this function. By the way, you can do this. You can always do this for testing purposes. You will find that using the chain rule, you will have to multiply the inner derivative, and then combining with this factor of 2, you get the integrand again. But even if any arbitrary additive constant is placed here, it will disappear after taking the derivative, and that's the reason why it must be allowed when when finding the general solution of such an indefinite integral. So that was rather standard. The next one is even simpler, but I would like you to know that because it's so simple, and by the way, it demands a so-called linear substitution, which is, you would say, the simplest case of a substitution. This is the reason why it sometimes you perform this substitution just without any comment. You don't really substitute. You keep in mind a certain theorem, which is given here, and by knowing and using this, you are not, well, you could say it's not necessary to explicitly perform the substitution. Let's just look here for the general case. Okay, so what we have is indefinite integral over f of ax plus b dx. So it seems that the inner function is a linear term, and it turns out that the primitive function then will always be 1 over a, where a is the linear coefficient of this inner term here, times, and now the primitive of the integrand. where I'm talking about the outer function inside the integral, right? So if you know this function lowercase f, if you have analyzed it and you know its derivatives, its primitives, antiderivative, and so on, and this theorem tells you you may just take the primitive of the outer function lowercase f, just this is usually called uppercase f, as you know, so this should be the primitive of lowercase f. You may do so, but you must be careful in two concerns. Firstly, always take the inner function over, so just keep it inside. And secondly, divide by the linear coefficient, because this is exactly what you need to do in order to, well, you could say, to make sure that the chain rule in the reverse direction is applied correctly. I give you a short little proof. You know that it's always enough to perform a little test by differentiating the result. If the derivative of this term equals the integrand, everything's fine. Now, the derivative of capital F with respect to x, of course, will be lowercase f. That's clear. By keeping this inner expression ax plus b. Then, but you have to go on using the chain rule when differentiating, which means you have to multiply the inner derivative. Now, the inner derivative will be a, constant a. And since this is the case, you would have a factor of a here, but this will cancel out against the a here in the denominator. So the whole additional factor will disappear, and you will have just exactly the integrand. So that's quite obvious. And the reason why this is so simple is that the inner derivative in this case is a constant. And that's why you can just simply divide it at this place without performing. As you see, what I do not do here is really explicitly substituting. Otherwise, I would have to say u equals ax plus b, and then du equals dx. And since the differentials will be equal, I am allowed to just replace the original differential by the new differential if I explicitly do the substitution. But since this is so simple, you can just do it in your head. So you see what I'm doing here? I recognize this is a square root of a linear term for x minus 5. So then I find out, this is a case for the linear substitution. What do? I just divide by a, and looking here I gave you the information, a equals 4 in this case. So that means, explicitly, it means that u equals 4x minus 5, but I don't perform a substitution explicitly. Instead, I just divide by 4. So that's my, it corresponds to this step here. And then I say, okay, I can do it, okay, if you wish. I can also say 4x minus 5 is replaced against u. So I write u. The square root is replaced by exponent of 1/2. As you all know, this is the potential, the power notation for a square root. Then I just construct my primitive by increasing the exponent by 1. So I get u power 3/2, and then I divide by the new power number 3/2. And also I have this additional factor of 1/4. By the way, you could say if I do it, I could, why not? Okay, if I use this, I can find that it was not correct what I said before. Du is not equal to dx, sorry, but it's equal, obviously, to a times dx. So in this case, du will be 4 times dx. And that's why if I isolate differential x here, I get differential x equals 1/4 times differential u. And that's why the factor of 1/4 originates by this substitution. But inside this box here, you can see this is just a standard method you can always use without thinking. Okay, so you can either do it or make the substitution explicitly. This is what I did then. So you see that here I just have to combine these factors, which is 1/4 times reciprocal of 3/2. Please be careful. If I pull this upward, or I take the reciprocal of 3/2, I get 2/3, 2/3. So I have 1/4 times 2/3, which means 2/12, and shortened, this is 1/6. That's what you get in the end. And also this special power notation may be replaced by the square root of this term u to the power of 3. Okay, this is perhaps, this looks a little nicer, and it gives you the connection to the original term. Also, I have performed the resubstitution in this step. So now, after all, n plus c is important, of course, the integration constant. After all, you find, and also I forgot it. No, I didn't. Here it is, plus c. Afterwards, you can recognize that without explicitly performing the substitution, you could also just have jumped from this to that. Okay, just by saying, or okay, you have to combine these factors. That's clear, but you don't need explicitly to perform this substitution. You can just use this scheme. I hope you got it. And now for the last one here, the third one. Now, interestingly, there are two rather different ways of solving it. There may be even more, but one of them is, well, first of all, we should exclude the gaps in the domain of this function. Okay, so since we divide by the sine of x, we know that the zeros of sine of x must be excluded. So all the zeros of sine of x are multiples of pi. That's what we know. So I demand that x is unequal to n times pi, n element n, and that's all. Now, there's well, actually, it was my spontaneous idea. There's a method for solving this without any complicated special substitutions. So, and this method is the following. I just expand this fraction. It's an idea, you know, it's spontaneous idea. You need a little creativity for solving integrals. And now the idea is to expand it by sine of x in upper and lower, okay, above and below. And then I get sine of x in the numerator and sine squared of x in the denominator times dx. Sometimes the differential is put in the numerator if there's nothing else. So that should not confuse you. So what I get is this. And then in another step, I replace squared sine of x by 1 minus the squared cosine of x. This is a standard procedure. You all know the famous the equation of the unit circle expressed by sine and cosine. You know that the squared sum of cosine and sine is always equal to 1. So that's what we use all the time. And also, I construct an artificial minus sign by just taking minus times minus, which is plus. Okay, that's a trick. And why do I do it? Well, simply because I want the numerator to be sort of the derivative of the denominator. You see, because what I have in mind the following substitution. The substitution will be, well, I could even here I could decide for the whole denominator to be substituted. In this case, I decided to take just the cosine, because it's the most inner function in the whole expression, right? Is the cosine of x. So let's just try. And if u equals cosine of x, I can say in differential form. Now you have been familiar with this technique, I hope, differentiating on both sides if you want. So you can always do it like this. If you have an isolated variable here, you just replace it by a differential, okay? So you build or you construct a differential. U gets replaced by du. If you do so, you must, on the other hand of the equation, if you find a term, you must differentiate it, okay, with respect to its variable. So I take the derivative of cosine of x, which is negative sine of x, and then I forgot to say, then I must place a differential of this variable behind. So that's the short method for differentiating u with respect to x and then separating the differentials. This is the fast method. Just u gets du, term gets differentiated, and then times differential. That's what you do, right? And also, please note that it always makes sense to ask yourselves, do I place a restriction on u by introducing the substitution? And the answer is yes, because the cosine of x, has a codomain of everything. Well, actually, is it? I don't know why. Yes. Normally, -1 lower or equal than u, lower or equal than 1. Since u is the cosine of x, it will be in the interval from -1 to +1, right? But the equal sign is not given here. Look back, because the restriction is that the zeros of the sine of x must be excluded, which are also interestingly, the maxima and minima of the cosine of x function, right? So because the maxima and minima of cosine are excluded in this way, that's why I told you that u must be actually inside the open interval between -1 and 1. This is, if you just want to solve the integral, okay, you don't care about this, but it's sometimes important if you want to make sure that your substitution is also really working. Okay, so that's more for the details. Now, see my trick? It worked in a way that I can now replace the negative sine of x times dx by differential u. So that's what I get. Everything disappears here above, except for du, which I replace. And in the denominator, I get 1 minus u squared, because cosine of x is u, so cosine squared of x equals u squared. Now, this is a very famous standard integral. That's why I just say handbook. Okay, take your handbook and find out where the primitive function will be actually in this case, if it's written like this, because usually you have an exchange of these two elements, that's why I have to place an additional minus. Just please consult your handbook yourselves, right? And you get the negative area tangent hyperbolic of u plus c. You know that this is the inverse hyperbolic tangent function, which is sort of a relative of the regular tangent. The so-called hyperbolic functions are also important. I don't have the time to explain them. But please also note the official notation is AR. It stands for area, and not to be confused with arc, which stands for arcus, used with the regular tangent. So this is the arctangent, which we used last time also, is the official expression for the inverse tangent, while the inverse hyperbolic tangent is called area tangent hyperbolic, or if you wish, also inverse tangent hyperbolic. Okay, that's how you should say. Now, so that's it. And also we find from here that the absolute value of u is lower than 1 anyway. And that means in the end, has something to do with the domain of this primitive function. We may just perform the resubstitution, which we always should do with an indefinite integral. And so we get negative area tangent hyperbolic of cosine of x, so plus c. And now the question is this primitive function defined everywhere except for the zeros, or let's say the gaps of our integral? Okay, going back here. And actually, it's interesting that exactly when x equals a multiple of pi for natural factor of n, exactly in this case, it would be not improperly defined. In other words, positively speaking, this function has a domain which is identical with its integral. And that's a good sign, okay? It's very, very often it's the case that the gaps of a function and its primitive function are exactly the same. So I don't want to go into detail now. It has something to do with the restrictions of the inverse tangent hyperbolic. And then don't Don't forget, this is a hyperbolic inverse function combined with a non-hyperbolic circular cosine. So it's not so easy actually, but well, it has to do with the fact that these are the maxima and minima, and they, as we found out that you will not take on these values anyway. So just let's leave it away. Now this discussion, at least we have solved this. And I want to even tell you there is at least another alternative approach which uses a certain special substitution, which is inside this box here. So I don't know if Martin told you in the lecture, but there are certain special substitutions which often help with difficult integrals. One of them is often used if you have an integrand containing sine of x and cosine of x, either one of them or both, and in a certain way which is not so directly clear how to solve it. Okay, and then it's quite surprising. It's surprising that this substitution where t, I call it t, it's just by fun, it could be u or v, however you call it, the new variable t equals the tangent of x over 2. You can, okay, it's easy to isolate x here if you want. X is then equal to 2 times the arctangent of t. That's not a problem, but it's a little problem to show that in this case, well, this is also not hard to do, because if you remember, the derivative of the arctangent is always 1 over 1 plus variable squared. So that's what I'm using here. The factor of 2 stays there, and this is again transforming this inverse substitution equation in differential form. That's what I'm doing here. And there's a restriction for variable x and also then for t accordingly. Not even now, but it's really an effort, quite an effort, to show that in this case, using this substitution, it turns out that the cosine of x will be this rational function of t, and the sine of x will be this rational function of t. So that's quite a lot of work to do to perform a proof of this theorem, if you want. Now that's an exercise by itself, but we won't do it. I just want to show you in short that it works. It works if I replace sine of x just by scheme. You can just use this as sort of a recipe, right? You replace in the denominator by this rational function, 2t over 1 plus t squared. Because it's in the denominator, I take the inverse fraction. Then I replace the differential x by, which is, by the way, almost the same rational function, but without the factor of t. This one times dt, this is here. Then I can cancel out these two terms, as you see in golden color, and also the factor of 2 here and here. What stays is simply integral dt over t equals ln of, well, absolute value of t plus c. And then resubstituting, I get ln of tangent of x over 2 plus c. And now, interestingly, this takes a little time to check, but take your time to do so. It's interestingly, this function has exactly the same domain as the one found before, where x is unequal to multiples of pi. So that's, you must look here. Actually, it turns, well, remember what are the gaps of the tangent function. And you may remember these are the odd multiples of pi over 2. That's a fact. So now, but since the argument is x over 2, I would have to exclude the multiples of pi to this end, or certain multiples of pi, so that if I, for example, if I take 3 times pi for x, then I have 3 pi over 2, which is a gap for the tangent function. So that's why I take whole multiples of pi, not of pi half, firstly. But then I find I have to exclude not only the zeros of not only the poles, which are the gaps of tangent of x half, but also the zeros of that function. Because the outer function, ln, natural logarithm, has a domain of its argument positive, right? So I get a problem in 2 cases. If the argument gets 0, which would be the zeros of this function, okay? And if it approaches infinity, where also the ln would approach infinity. And that's why the poles and zeros of tangent of x over 2 have to be excluded, which means in the end that all the multiples of pi have to be excluded. You don't have to understand this immediately now, you can check it, okay? But now, why did I tell you this? Well, because it's a good hint at the fact that this is a valid primitive function also, because now if you compare with our previous result, these are two obviously rather different expressions. Now it's really a hard task to show that this function in the end is exactly the same as this one. It has to do with the fact that the area functions, as well as the area sine hyperbolic, as the area cosine hyperbolic, and also the area tangent hyperbolic, all of these are modified natural logarithm functions. So that's a good hint at that you can, in some way, you can transform it to be the ln of something. But then to transform the cosine into this tangent of x half, that's really a hard task. I gave you in red color, just in case you want to take your time and take the effort. This as a home exercise, prove the equality of the two results. But it's not easy and it's not necessary, just in case you find the time. Okay, so now that was a little lengthy, but that's it.